we're going to walk through how to find the oxidation states. First, let's talk about what an oxidation state is. An oxidation state is a theoretical construct. This means it's not real, but it's a really useful concept for us. An oxidation state is where we pretend that every electron is owned by an atom, and then when atoms bond together, we assign that electron to one atom. So even if you're sharing, we say who has a larger share of that electron, and we just give them that electron. This is really useful because then in a chemical reaction, if we assign the electron to one element, we can see where that electron is moving, and we can track the movement of the electron. Because all chemical reactions, with the exception of nuclear chemistry, come down to the movement of electrons, the trading of electrons or charges, this becomes a really powerful tool. There's a lot of different ways to understand an oxidation state. I think the simplest is to memorize this list of priority. This is like the A list, okay? So if these elements are all in line to get into a high-class party, the first people on the list are going to get in first, and the lower you are on that list, the less likely you are to get in. So if you just know this list, you can apply that to any compound or ion, and you can know what their oxidation state is. So the priority list is that metals come first, and then hydrogen, then fluorine, then oxygen, and then we go from group 17, 16, 15, 14, work our way to the left across the periodic table. Notice group 13, etc. aren't listed because metals are already listed at the top of the list. And the thing to know is if they get their priority, then they choose to have their ionic charge as their charge. So if they have priority, then they will have their oxidation state and their ionic charge the same. So let's try a couple of examples. Let's start with the dioxygen difluoride. The first thing to do is decide who here has priority. If you go back to our list, we see that oxygen is number 4 and fluorine is number 3. So fluorine has higher priority, which means fluorine will take its ionic charge as its oxidation charge. So the ionic charge of fluorine is 1-, which means the oxidation state is -1. Then, because this is a neutral compound, and we know it's neutral because there isn't anything written right here. If there was a charge written here, then it would be an ion. If there's nothing written, then the charge of the overall compound is neutral. The oxidation state of fluorine is -1, and we have 2 fluorines. Then we have 2 oxygens, and the oxygen in this case is going to be the poor schmuck who has to make up for whatever charge the fluorine wants because fluorine has priority. So I just give it an x, and then we can solve this equation algebraically. So 2x is going to be equal to 2, meaning the oxidation state of the oxygen would be +1. Now that's super weird. We're used to seeing oxygen with a -2. So in this case, its oxidation state would be different than its normal ionic charge. And the reason for that is because it's paired with fluorine, which has a higher priority as far as oxidation states go. All right, let's look at an example with an ion. So the charge of this phosphate ion is -3, which means the total charge of this compound has to equal -3. The first thing we do is we look and see, okay, who has priority, oxygen or phosphorus? If we look at our list, oxygen is number 4, phosphorus you find in group 15. So oxygen has priority in this case. Oxygen's priority means it will have its ionic charge. The normal ionic charge of oxygen is -2. So that means the charge of the oxygen is -2. We have 4 oxygens, and then we only have 1 phosphorus, and we don't know what its oxidation state will be. So we put in an x. Then you can solve this algebraically. 4 times -2 is -8, equal to -3, so x is equal to +5. Okay, so let's try the aluminum hydroxide. First, you can ask yourself who has priority, aluminum, oxygen, or hydrogen. When you look at your list, we have oxygen, we have hydrogen, and aluminum is a metal. So aluminum gets the highest priority, meaning aluminum will have its ionic charge as its oxidation state. Next on the list is hydrogen. So hydrogen will have its normal oxidation state. And then we can solve this algebraically for what the oxidation state of oxygen is. Generally, you always solve for just one element that will have an oxidation state different than its ionic charge. I'm going to show you an example in just a second and talk about the exception when there might be 2. Okay, so the total charge of this will be 0 because there's nothing written here, so it's a neutral compound. Then we have 1 aluminum with a +3 charge. We have 3 oxygens with an unknown charge. And we have 3 hydrogens with a +1 charge. So then we can just solve this algebraically. So we have 3 plus 3x plus 3 equals 0. So 3x is equal to -6. So x is equal to -2. Notice how I'm writing the oxidation state of each oxygen. Even though there's 3, I'm writing the oxidation state of just one of them. Okay, now I'm going to level up. So those are normal, and these last two are a little bit more difficult examples. So in this one, you'll notice I have 2 polyatomic ions. In all of the rest of these, I had a maximum of 1 polyatomic. So I had 1 polyatomic ion here, and this itself is a polyatomic ion. If you have 2 polyatomic ions, then you need to solve for 2 which have an oxidation state different than their ionic state. Anytime you have a polyatomic ion, you can always solve that separately rather than as a compound as a whole. So if you have a polyatomic ion, then you can say, okay, NH4 ammonium has a +1 charge. So I can solve for that. And separately, I can solve for the oxidation states in sulfite, which has a -2 charge. So I don't have to do the polyatomic together with the whole compound. I can do it separately. The first question is, who has priority? So we go back to our list and we see that nitrogen is in group 15 and hydrogen is way up here at number 2. So hydrogen will have priority. So our hydrogen having priority will take a +1 charge. We have 4 hydrogens times that +1 charge. We have only 1 nitrogen. We don't know what its charge is. And since it's an ion, its charge goes right here. So the x is equal to -3. Do the same thing with sulfite. The first thing we do is go and see what our charge is. Sulfur, which is in group 16, and we have oxygen, which is here at number 4. So oxygen gets priority over sulfur. So the oxygen will take its normal ionic charge, which is -2. We have 3 of those, and the whole thing will be equal to the charge of the ion. Then we have 1 sulfur, which will say its oxidation state is X, and we can solve for what it would be. And in this last example, we have molybdenum 6 carbonate. And this one is a little bit different because molybdenum is a transition metal. For the transition metals, most of their ionic charges are variable, or they can depend on what they're paired with. It's still a metal, and it will still get priority. If we go back to our list, molybdenum will have the highest priority because it's a metal. And then we have carbon, which is way down here in group 14, and we have oxygen. So the order of priority will be the molybdenum, the oxygen, and lastly the carbon. Now, we said if it has priority, it takes its normal ionic charge, but with a transition metal, they can have more than 1 charge. So you just have to look at the compound and say, okay, what is the charge of that molybdenum in this whole compound? We know the charge of carbonate is -2. We see that there's 3 carbonates, so the total negative charge here is 6, meaning the total positive charge in this compound also has to be 6. Since there's only 1 molybdenum ion, that means the charge of that ion itself is going to be a +6. Because it gets priority, that means that it will also have that same ionic charge for its oxidation state. So we have 6, but there's only 1. The carbon is the one that we are unsure of, so we have 3x, and the oxygen is -2, and there are 9 oxygens with a -2 charge. Because it's a neutral compound, the whole thing will equal 0. Then we can solve this algebraically, so we have 6 plus 3x minus 18 equaling 0. 3x equals 12, and then x will equal +4. So the oxidation state of that carbon is +4.